Okay, hi everyone. So I want to start by setting a few ground rules for this talk and talk about what this talk is not going to be about. So I'm sure many of you are aware that OpenStack has been working for a while now to get a lot of the infrastructure components of OpenStack running on top of Kubernetes. We are not going to talk about that at all. If you want to talk about that, I'm certainly interested, but it's not this talk. What we are going to talk about is some real life experience of running a container platform in OpenShift on top of OpenStack. In a research and education environment.
Hi, my name is Rob Barron. I am with the Massachusetts Open Cloud. This is a collaborative effort among 5 Boston area universities: Harvard, MIT, Boston University, Northeastern, and UMass, as well as some corporate and nonprofit partners. Our basic goal is to provide an open cloud exchange, open cloud marketplace, to which in order for us to do research in how to deploy such a marketplace, we found that we really need to have our own OpenStack cloud, of which we have put OpenShift on top of. Our cloud is actually based at the Massachusetts Green High Performance Compute Center. It's 8,000 square meters of compute space, 15 megawatts coming in, 75% coming from a hydroelectric plant that is very similar to where this is located. So that's where we're hosting the cloud.
Thanks. So my name is Dan McPherson, by the way. I work for Red Hat. I'm an engineer with Red Hat, and I've been working on OpenShift since about 2011. It's actually the 3rd engineer in total to work on the project. I recently moved to Boston, actually, where the MOC is located. And I've had the pleasure of working with a lot of the folks there at the MOC. It's a pretty incredible setup that they have. I know I'm quite jealous, at least from whenever I was a student at university. We had nothing of that sort, so it's really a neat facility. So I think what would be useful here is for us to talk about some of the use cases that we have for a container platform on top of the MOC. And we'll start there and we'll dig into the details afterwards. So one of the things that we're doing is the CRIS project. So that stands for the Children's Research Integration System. And it's a web-based medical imaging platform that was originally developed out of Boston Children's Hospital, which is one of the premier hospitals for children in the US and the world even. And what the system does is it takes images, usually in the form of MRIs, and does some sort of processing on them. So an example of this would be they might have a series of images where the patient might be moving, and they want to be able to take those images and coalesce them into a single image that is usable, and to make it so the doctors can interpret it in some way. That particular type of application is called registration, and it can take a really long time to work. So somewhere in the range of 10 to 24 hours quite often is how long these things take. And there are ways to be able to improve this. So you can obviously scale out some of these things to run them on multiple systems at the same time. There's also things like adding GPU enablement that can help quite a bit. And I should mention too, the CRIS project itself is open source, and so it's really a good fit for both the MOC and for Red Hat to be able to work on it. And so what the CRIS project has done, I should mention too, it originally started running on top of VMs, and that was roughly 3 years ago, whenever that work was taking place, to be able to get the CRIS project to run on top of OpenStack inside the MOC. And what's happened since then is that the container world has sort of taken off. And they've realized that it would be helpful from a performance point of view, as well as from a distribution point of view, to be able to use containers instead of VMs. Performance just because you can start containers a lot faster than you can start VMs. And then from a distribution point of view, using Docker images to be able to distribute everything is a really great system. And what the goal really of the CRIS project and the MOC here is to be able to sort of democratize the space of what it means to do image processing. What's previously been the case is every single one of these different image processors would essentially have to build their own system to be able to manage scale, manage GPU or other hardware acceleration. And it means that they're all isolated so that there's not a common environment to run them across. And what the MOC is really trying to do is make it so that everyone has a standard platform to be able to run across. And they're doing this by taking OpenShift, running on top of OpenStack to give a standard environment everyone can scale for. And I mentioned GPU acceleration, so that work is currently ongoing inside of OpenStack and OpenShift to be able to enable it for the whole stack. The other thing worth mentioning for Chris, as far as a big benefit, is the Cube scheduler lets you take advantage of Slack resources. And so the MOC has an OpenShift deployment now, which we'll talk through here. And it's the case that there's some number of nodes. They have various priority processes running on them. But the MOC wants to be able to use those resources as well as they can. So it's possible to schedule high priority resources that are guaranteed to be able to get however much they ask for, and take projects like the Chris project, which may be running thousands of jobs at the same time, and take advantage of the Slack resources and say, if one of those 1,000 jobs ends up on a machine that's too busy, it may get killed and launched onto another machine. But it means they can utilize the whole cluster in a really efficient way. Another really interesting project that's running on the MOC is the Open Dataverse project. So this is based on the Dataverse project, which is a system that was developed out of Harvard. It is a community-based system now, though, where researchers will submit their data sets for review and public consumption. And the MOC has taken this project and deployed it at a much larger scale. And the idea is that they want to be able to make it available for researchers to be able to come into the MOC and use the very large data lake that they have, a 20 petabyte data lake, to be able to do research on that data and use the compute resources of the MOC to run the calculations. So these include big data tools like Hadoop or analysis tools like Spark, as well as ML and AI type systems that are coming into play as well. So this has been happening on virtual machines for the past little while. What's happening now is OpenShift has been added to the MOC running on top of OpenStack, and there's a technology being developed with Kubernetes and OpenShift to be able to have a service broker where you can connect to external services. The way we see this working going forward is projects like Spark, which are being introduced into container environments, again, because of the efficiency that containers add to that equation. We see it being the case where you can connect to the data lake with the service broker API to be able to, in the same way that you could previously launch VMs to run jobs against the data lake, you'll be able to, with the service broker, be able to connect to the data lake and run those jobs in an OpenShift environment.
So our principal two communities, or I should say, we're an academic-based organization. We provide compute services to students as well, taking classes, as well as researchers who are trying to get compute power, get work done. The Chris project and the Dataverse project were actually both class projects. There were a number of class projects involving both of those projects, and there are a number of researchers working on those projects.
Okay, so I think it would be really helpful if we dig into the technology a little bit first, just to make sure everyone's on the same page. I want to do a quick poll, though, before I do that. So how many of you actually are aware of OpenShift at this point already? Pretty good number. How about Kubernetes? Keep your hands up, actually. Okay, and what about Docker and containers in general? Okay, so most people. Great. Okay, so let's start with a little bit of details about OpenShift. It's a supported distribution of Kubernetes. We do add a number of things sort of on top and on bottom of Kubernetes. So on the operational side, we add a number of frameworks that don't come out of the box with Kubernetes, but give you a complete system. So things like a logging stack and a metric stack, and also a management system in cloud forms. And then on the other side, we take Kubernetes, which starts basically as a deployment platform, and we connect that to be able to run builds on the platform and be able to connect it to your source code running somewhere in Git, or host it somewhere in Git. And then OpenShift itself is distributed in three forms. So it's a hosted platform in the form of OpenShift Online. It's a managed solution in the form of OpenShift Dedicated. And then it's also an on-prem product in the form of OpenShift Container Platform. And that's what actually runs on the MOC is the container platform. So going one level deeper, Kubernetes is a cluster orchestration tool for Docker or OCI containers. It was originally introduced by Google back in 2014. And by many measurements, it's actually the most active project that exists on GitHub. And this stat's actually from 1.5 in Kubernetes. We're currently up to 1.8, but it gives you an idea of how much work has gone into it. But up to this point, it's been over 500 person-years of work that's gone into Kubernetes. And we're very proud that Red Hat is the #2 contributor behind Google. Okay, so Docker and OCI. Docker is the container runtime and image format. It was originally launched in 2013. It took what was a container system in Linux and made it really consumable by someone other than a kernel developer, essentially. OCI came around and was established in 2015. A lot of corporations came in and wanted to standardize what a container meant beyond just a single corporation. And Docker worked really well with that group and donated the vast majority of what they had done. And now OCI is sort of what, again, defines the standard of what is a container. Okay, so a container itself. A container is a Linux process, and then it's wrapped by a number of isolation technologies. So SELinux, Cgroups, and Linux namespaces are the main three. This provides multi-tenant isolation on a single host, which gives you a lot of advantages. The nice thing about this is that it adds near zero overhead, especially when you compare it to a virtual machine. And the way it does this is that the little diagram at the bottom there describes how in a single host you have lots of containers all sharing the same Linux kernel. So you could have, for example, a database and a message broker and some web framework, each of them running inside of separate containers, all of them sharing the same kernel on the same host. And so you get a lot of efficiency this way, a lot of density out of the system. Okay, we're gonna go one level deeper just to get go all the way to the bottom here. So SELinux. This is what is the main security mechanism that exists with containers. It provides access control through a whitelisting mechanism. What that means in basic terms is with SELinux, you have to describe exactly what you want to allow to happen on the system. So once you've defined that, you know nothing else can happen that you haven't explicitly allowed. We do this with containers in a very specific way with multi-category security. This lets us do a dynamic form of allocation. So for anyone familiar with SELinux, the normal way SELinux works is you have a policy, you compile that policy, and at that point it's a very efficient way of managing the system, but the compilation is quite time consuming. So what you can do is dynamically add these labels to every process that you instantiate, and in this case that process maps to a Docker container that's running, and get that same level of security without having to manage the policies you previously did. Another technology we use is Cgroups. It's another kernel feature. It lets you constrain resources, so things like memory, CPU, I/O, and it's per process, so again, per container that works. And it's the thing that lets us get all the pretty graphs that make each container feel like, again, it's its whole machine by itself. And then the last one, and probably most important from an experience point of view, are Linux namespaces. So there's 7 or 8 of these total, I forget exactly, but the 4 easiest ones to sort of get an idea of what they do, we'll talk through this here. So the first one is the mount namespace. And the mount namespace means that each container can have directories from the host mounted into it that are unique to that container. And so in this case, /share might be mounted into one of the containers, but not all of the rest. The PID namespace means that every single container starts again at PID 1. And this PID 1 is different for each container, and it's different from the host as well. And it means that if you run a PSEF on inside of a container, you're only going to see the processes that are actually inside of that container, not from the host and not from other containers. For the net namespace, it means that each container gets its own 127.0.0.1 and can bind to whatever port it wants to bind to inside of itself. And then the user namespace means that each container has its own root, although that root is not the same root as the host, and again, different across each container. So each of those technologies are sort of combined together to be able to give you the experience of feeling like you own your own host, but again, at a much lower overhead than what you get with virtual machines. Okay, so let's talk a little bit more now about why OpenShift and Kubernetes really makes sense inside of the MOC. So first, this isn't so much a positive, but we have to mention it because it's definitely not a negative. and that's that anything that runs inside of Linux will run inside of a Linux container. So that's just starting from we don't lose anything by going to containers. But there are a lot of ways where OpenShift and Kubernetes really sort of help your application. So I mentioned with Chris before, but containers give you a great way to be able to distribute your application. And that's in two ways. One, it's a nice image structure, but it's the case, it has image layers, which mean if you are only constantly changing that top layer where your application lives, you can push that code around, and it's no bigger than your code is. It's not the size of the operating system and everything below it, which is the case with the virtual machines. You're also isolated from dependency issues because of some of the technologies that I mentioned before. So you can have two containers running on the system, one of them running Python 2.6, one of them running Python 3.5, and they have no idea that they are running different versions there. Kubernetes also has a declarative config mechanism, and everything in Kubernetes and OpenShift are declarative. What this means is that you essentially tell it, here's what I want the system to look like, and then in the background, it's constantly making sure that that becomes the case and stays the case. So another piece is that using Kubernetes and OpenShift makes everything easy to operationalize. And the reason for this is that it slightly limits the world of what's possible to do compared to what you get with virtual machines. And not by a lot, but at least to the degree that there are standards that have been created. So an example is with Docker, there's a common standard or pattern, I should say, where you want to have a single process that you launch per container. That tends to map to some application component. That means that the standard error and standard out from that process are the logs that you want to capture. And you know that those logs are relevant to that one process. The same thing for metrics. You know that if you capture the CPU and memory for a container, you know you're capturing it for a component of a process. When you're dealing with a virtual machine, you don't know how many things are running on that virtual machine. And being able to say, this machine is using this much memory and CPU only tells you that's at a machine level or at a VM level and not at what's running inside of the host. So all of those things make it so that we can do things like have a standard metric system, have a standard logging system, and make it really easy to have the operations team and the users be able to interact in a very sane way without having to constantly communicate of how do you monitor this new application. It's also the case that OpenShift really provides that complete application lifecycle management. So again, I mentioned we connect all the way from your source code all the way to how you manage an application running in production. Okay, so as far as utilization of hardware, there's a few things that OpenShift also does there that really help. So one of those pieces, which I referred to, is the fact that the kernel is shared. And so it means if you do want to launch an application that has lots of different components associated with it, you can have each of those components have their own container, but not have to have another host operating system that runs for each one of them. And so, if the host operating system takes a gig of memory and you have 10 components, previously that would have been 10 extra gigs of memory you had to run that now you only need 1 gig of memory for. So quite a bit of savings there. And then the other piece is overcommit. And again, we're taking advantage of this with the Chris system. But because of overcommit and the quality of service tiers, it means that you can pack a lot more resources into the system than you can otherwise. And then last layer, which is very important actually to the MOC use cases and the university use cases as well, is container idling and auto unidling. And what this means is that you can put a component of an application to sleep, and whenever someone makes a request to that application, it will wake it back up again. So during the time period it's asleep, it basically takes zero resources from the system. This is incredibly valuable for university-type use cases because you have lots of students, and those students have the equivalent of a class one semester where they may need to host a website. And let's say they're a freshman. If they're there for 4 years and no one knows what's running on that system, it's difficult to shut it down, but it's a lot easier to be able to idle it and know if they come back to it, it'll wake up for them, but otherwise it takes zero resources. So a really huge advantage. Okay, so what I just talked about is more from the perspective of what it means for the operators to be able to manage the system and the benefits they get. There's a lot of benefits to the students themselves. So one of those pieces is that the students get a lot of self-service features. And so instead of having to deal with an operator to be able to get something deployed onto the environment, The way that OpenShift and Kubernetes are built, it's designed so that you can have a DevOps model. And what that means to a student is the student gets to manage the system from end to end without a whole lot of work on their part. If you want to compare this to what you get with an OpenStack environment, let's imagine that you have 10,000 people, and for the 5 universities, that's a close number, I think, to what you could expect as far as the number of technical students that might be using the system. And you have to wonder, 10,000 users coming into a Horizon environment, how many of them are actually going to understand the concepts that are there? It can be quite complicated. And if you think about this from the perspective of how do you allocate projects, you sort of have a couple of options. You can give each student their own project, and if so, you end up with the issue of, very similar to the problem of each student now has a computer under their desk, and you don't know what's running on that project, you don't know whether what they've made is secure, and it can be a little scary to deal with. And figuring out when do you take that computer back away from them, or when do you give them a smaller computer or a bigger computer, it's difficult. The other alternative is that you could have shared projects where you have admins that have to be responsible for managing that quota, managing that security. And that also is quite difficult because with 10,000 students, you might need 100 or 1,000 admins to be able to manage it. And finding that many people who are responsible to be able to do it is not an easy task. From a security point of view, obviously, getting students to manage firewalls is not an easy thing. What Kubernetes and OpenShift do is they take a secure by default stance. And so there's a lot of features that are built in that you can't override as an end user. And as you're using the system, it's actually difficult to build something which is insecure. And so a random example of this is that we, by default, keep users in OpenShift, keep users from running something as root. And that's because currently today, and this will hopefully get fixed eventually, but currently today, if you allow people to run as root inside of a container, it is possible for them to escape out. And what we do is, by default, keep people from being able to do that type of thing. And there's a long list there of other technologies that we use and provide that really do provide the secure system by default. And then I mentioned overcommit before. It's also worth mentioning a benefit to the students is that because of overcommit, it means that they can be given more resources. Because in the end, it's a finite number of systems. You're giving out quota based on average consumption. And if average consumption is lower because of overcommit, then obviously you can be more liberal as far as how much you allow them to use. Okay, so up to this point, I realize I've talked almost entirely about what the container platform is. We're going to sort of transition now into why we've picked OpenStack for this, and why it makes sense to build a container platform on top of OpenStack. I'll start with mentioning that we sort of view OpenShift and Kubernetes as the platform that runs everywhere. So it standardizes deployments really across all the different cloud environments, including on-prem and public cloud. But OpenShift and Kubernetes do not ever solve the infrastructure problem. We have to have some environment we deploy onto. And you can deploy it onto bare metal, but you miss out on a lot whenever you do that. So what we really believe is that in the end, we want to be able to have a private cloud story that is sort of unifying and as good as what you get with the public clouds. And that's what OpenStack is to us. So some of the benefits. So dynamic storage provisioning. And this is a good example of where Kubernetes doesn't provide the infrastructure. What you get with dynamic storage provisioning, which was GA'd actually relatively recently in Kubernetes, is the ability to, as a user requests storage, it will check their quota, and if they have enough quota left, it will dynamically allocate the storage for them. The only way that's possible is if you have an environment that brings that storage in an API to you that you can instantiate. What you get without dynamic storage provisioning is pretty painful, where you actually have to pre-allocate volumes that then users can claim those volumes. So to an administrator, that's a nightmare. With OpenStack, because of Cinder, we can make it a great seamless user experience and not have to disturb the admins, and the users get what they want right away. We also use Swift inside of OpenStack, so we use this for the registry. We also take advantage of it from the Chris project to be able to use it directly, because having object storage available to you is pretty powerful. I mentioned the service broker before, and really we want for everything within OpenShift to be able to connect to all of the services within OpenStack. And you get the same type of experience in all the public clouds, where there's a vast array of services that are available. And whenever you go to an on-prem environment, being able to have a similar experience is pretty priceless. We also use Keystone to be able to do authentication. So that's the same Keystone that's used for the OpenShift environment as is used for the OpenStack environment. It's really up to an administrator how they want to configure that. You could make it so that every user gets access to both environments if you have those sorts of users. You might have some users which are less sophisticated, and so you might not want to give them access to OpenStack, and you only want to give them access to OpenShift. But at least you only have to have one auth store either way. And then one of the other big benefits is the potential for us to be able to do cluster autoscaling. So, and again, pointing out that OpenShift and Kubernetes don't manage the infrastructure. They manage overcommit, they manage scheduling in Kubernetes and OpenShift for every node that's been added to the OpenShift cluster. If there are too many resources in the system, OpenShift doesn't currently know how to get rid of those resources. I mean, if there's not enough resources, it's just going to stop scheduling things. So what you really need is the ability for something to recognize, I know how to allocate more resources, I know how to take resources or VMs nodes away, and be able to auto-scale up and down accordingly. We're sort of getting to the point where this feature will be added into OpenShift and Kubernetes, but it can't be possible unless you understand the infrastructure that exists. And in an on-prem environment, we need an OpenStack to be able to make that happen. Okay, so there are a lot of ways that this could be better. Currently, whenever you're running OpenShift on OpenStack, you're usually running with a doubly encapsulated network. And so that's not a great thing, right? You have two SDNs that are running on top of each other and a decent bit of overhead that comes along with that. And so there's a project that's already ongoing called Courier that's working to fix this and essentially make it so that when OpenShift is running on top of OpenStack, it is reusing the SDN that comes from OpenStack. So that'll be a great performance improvement. I mentioned dynamic provisioning before of storage, but there's still a lot more that needs to happen around storage. One of those things is snapshots. This is something that Kubernetes is working on, and it'll work with the various public cloud providers, but in an on-prem environment, OpenStack is our main case where we can manage these types of features. We also really want automated backups. So this is something that's not happening yet, but it's a relatively complicated space. So in OpenShift and Kubernetes, there are lots of different volumes that are mounted. There's a wide variety of them that are mounted for the nodes, so things like Docker storage or the operating system volumes itself. They get mounted in. And then the containers themselves, related to the PVs that I was referring to before, they also are their own volumes that get mounted in. And whenever you want to back up the system, it's relatively straightforward in that you want to back up the PVs that are mounted into the application. Whenever I say PV, by the way, I mean it's persistent volume, if I haven't said that. But yeah, you want to back up the PVs related to the applications, but you don't really want to back up the volumes that are mounted for the node itself. And that's because OpenShift and Kubernetes take the same mindset that OpenStack does, which is you should be able to throw the nodes away, launch a new node, remount the storage into it. And that works too for the applications. You're also able to remount in the storage for the applications, but you probably care about the data that's there for the applications, and you probably want to be able to back it up in a sane way. Having an OpenStack be able to understand the container platform well enough to be able to know which pieces of that are relevant to backup and which pieces are not would be an incredibly valuable thing. Another piece is the install and upgrade. I think we're going to be in the state for quite some time where we have VMs and we have containers. And right now, there's not a lot of great integration between those two, where whenever an administrator has these two systems built on top of each other, they essentially have to manage those upgrade and install cycles on their own. And it's a little tedious. I can imagine a world in which you, for example, could coordinate the upgrades of the OpenStack components along with the Kubernetes or OpenShift components in a more sane way than you can today. I think a huge area for improvement as well is in the UI. So a couple of examples. One of them is having OpenStack be able to understand in detail the container platform that's running on top of it. So container platforms generally consist of some control plane as well as some number of nodes. And being able to have OpenStack understand that these are my control plane components, or maybe my infrastructure components tied to my control plane. And these are the nodes that are involved for the compute portion of it. Would be very valuable, I think, to an administrator to be able to make that segmentation. It's also the case that from an application point of view, I've talked about how you might have one application that spans containers and virtual machines. Being able to understand what an application is from an OpenStack perspective, I think would be quite valuable as well. So as an administrator, if knowing that these VMs have containers running on them, another set of VMs have images running on them, maybe they're also talking to the Swift object store as well at the same time. Know that those things are interrelated, and know that when I delete something, I'm affecting an application in some way would be quite valuable. And then lastly here, I know a lot of what I've stated here is that the use cases that previously existed for VMs have been moving to containers. And I'm not trying to sugarcoat that. I think that's a reality. At the same time, there are lots of cases now that are coming up for function as a service and serverless that all of 2 years ago, everyone would have said containers are the only way to do that. And now the serverless technologies are coming along, and they look quite interesting for a lot of use cases. And so I think what needs to happen is that from a user's perspective, there are going to be cases where all three of these technologies are the right choice. And what we're doing at Red Hat is we are trying to make it so that the serverless solution that we runs well on top of our container platform. And we also are obviously making it so that our container platform runs well on top of our VM infrastructure platform. And in the end, what you want is for all of those things to be integrated well, to not compete with each other, so it's obvious which choice I should make for which technology I'm trying to run. And then as a user, you really want it to be, I can go to any one of those platforms and understand that there is a way to be able to nicely link to the other platform and understand how everything interrelates together. Okay, so I think that is the end, and I appreciate everyone coming. Hopefully that was interesting, and we can take questions. Yes?
How do you manage quotas for storage quotas and other plans?
Yeah, so in OpenShift you have a project, and by default, or you can set it so you have a default quota for that project. Every single resource has a quota on it, and so you have a quota for how much storage you want to allow. And storage is a little complicated because there's something called storage classes. So you might want to have a quota for how much fast storage they get, or how much magnetic disk storage, or how much, name whatever type of storage you want. There's a lot of options there, but you have a default that gets associated when you create your project, and then you can modify that as an administrator if you want to give particular people more access. Other questions? Yes?
Sorry, another quota question coming from academic background. Is there flexibility to say quota for a user or for a project, say 3 months or 6 months, and the kind of mechanisms to request quotas and approve quotas and that kind of workflow?
Yeah, I'll repeat the question there. So the question is there a way for users to be able to request quota over time, or ask for more resources, essentially? So there is not a built-in system in the platform that can do that. We have had actually a number of users of the product who have deployed it have built systems like that for themselves. There's obviously APIs you can set quotas, and so putting some UI or whatever you want to on top of the system to be able to request that sort of thing, it's a very doable system. It's specialized enough that doing it generically for everyone is not something that we've been able to do yet, though. Other questions? Yes, one more.
What's the fast service that you use?
Sorry,
Which kind of fast service do you use on Red?
are you saying PaaS as in PaaS?
As a service.
Oh, sorry. Yeah, so any of them will technically run. The one that Red Hat is making a bet on is OpenWhisk. We're currently building that out on top of OpenShift now. And there's some really neat things that are happening around function as a service as it relates to containers. So there's two sides of this. One is that with function as a service, you really want to be able to have a good ecosystem around it, right? So if you just built a function as a service by itself with no ecosystem, like if you don't have an object store, for example, it doesn't do you a whole lot of good because there's not a lot of interesting things you can do. And then name all the other technologies that exist in Amazon that made their Lambda solution so interesting to everyone. So that's sort of the starting point. The other side of this that makes building it on top of OpenShift so valuable, or Kubernetes in general, is that building a function as a service system, you have to be able to run that in a backend that makes it efficient. And how would you do that? Well, would you, every time someone registers a new function, start a new virtual machine and leave it running forever? That's not going to be efficient at all. You have to have some way to be able to, when someone has a function, launch it. If they're using it, leave it running. If they're not using it, shut it down. And containers are great for that because they launch really fast, which is half of the problem. And then with things like idling, or with OpenWhisk in our case, we might build it into that feature, or into the library. We can be able to say, this particular thing is not being used, therefore shut it down. If they make another request to it, then we'll start it back up again. But you really got to be able to manage your resources efficiently and still be able to provide the good user experience of, I just write a function and it runs somewhere at a relatively low cost. Okay, any other questions? Yes?
What about the notion of jobs and Kubernetes? I've played around with it much myself, but the idea of batch processing, doing things that otherwise not even done on HPC, but that's super
Yeah, good question. So the question is about what's happening in the space of jobs and HPC as it relates to Kubernetes and OpenShift. We get that question a lot. So I'll approach it from two sides. So there's the hardcore HPC side, which exists. So if you're currently using Slurm and Singularity, you may not say, yes, I'm absolutely going to jump to Kubernetes and OpenShift. However, if you are in the space of, I'm doing things that look a lot like HPC, and I like Kubernetes and OpenShift already, then Kubernetes and OpenShift look a lot like those other systems, right? We have had a job system in Kubernetes now for a few releases, and they're adding more features around that. Cron was the latest thing, and they're doing more batch-type features there as well. And so you're getting a feature set which is becoming more and more competitive with what you get on the HPC side. Whether Kubernetes and OpenShift will truly compete in HPC, or whether it will be only the case for people who are already using Kubernetes and have some HPC-like scenarios decide to start using Kubernetes instead of building a new system, a new competing system. I don't know which of those two will happen, but they are definitely converging to some degree. Yes?
Could you talk to dedicated storage nodes on storage?
Yes.
Can you need SSD spinning as opposed to putting those layers in the compute nodes? So
I'm not positive I got the question. Can you try one more time? It was hard to hear part of it.
So dedicated storage racks as opposed to putting storage in the compute nodes themselves.
Oh, I see. Yeah, so I didn't clarify that, I guess. In OpenShift, in Kubernetes, all of the storage has been remote storage, actually until very recently. It's actually not on the compute nodes, with the exception of, we actually do provide something called container native storage, which is Gluster running on OpenShift itself. In that case, you could be consuming the storage from the nodes, but all of these cases are the same as the OpenStack scenarios where you're mounting in storage from a remote location. Just now for this next release, 3.7, local storage is being added for the first time, so you can schedule something to run with local storage, but that's only a recent change. Hopefully I answered your question. If I didn't, please come by after. All right, any other questions? Yes?
With the doubly encapsulated networks, what's the performance dip you see with that?
Yeah, okay, so I can only give anecdotes. I don't have and it's going to vary by your environment is part of the problem too. I can tell you that, and also the other thing, it varies a lot by how fast your network is. So if you're running a 1 gig network, the overhead's very low for these things. If you're running a 10 gig network, you start to see it. And those numbers might be in the range of 20 to 30% on your total throughput. And that's overhead on throughput. At the same time, you're also getting a pretty big hit to your CPU to do that. By the time you get up to a 40 gig network, I don't have the number, but it's even higher. And so there's quite a bit of room for improvement. Any other questions? All right, if not, I think we're out of time anyway. So thanks everyone for attending.